Okay, next lesson there. Weight, please. I'll write this down. Yeah, do you want, your one's the one on the left. Do you want to turn it on?
No, but I didn't want to make a mistake or anything. I got a little.
That one?
Yeah, I knew that, but
wasn't 100% sure. Okay, do you write that down? Weight. The projector.
I think that's the projector.
Okay, continue. Yeah. Okay. Is weight a word you know?
Yes.
Weight. The weight of something.
Yeah.
Okay. So we'll start with the definition of weight. Gravitational force is the force of attraction. Well, before you write it down, so we have this type of force called gravitational force, and it's between all mass, all matter, and usually only happens when it's very large. So for example, if you have something like the Earth, then the Earth starts to pull other things to it. So there's this force that the Earth has that can pull other things to it. What else has it? The sun has it. The moon has it. And we have it. Very small. Very small. But everything has the ability to pull other things to it, but we don't notice it until it's very big. So gravitational force is the force of attraction between all matter. Normally, you only feel it when it's very big, like the Earth, the Moon, the Sun. Okay. So if we can get this definition, gravitational force is a special type of force. Okay?
Yeah.
You have this? Now I said it's between all matter, and as you were saying, we all have it. And in fact, we only notice it when it's really big. But there are some experiments that people have done to try and detect it with smaller objects. So I know there's like one experiment where you have a giant sphere of like 1,000 kilograms. And even this is too small. But if you have very, very, very sensitive equipment, it can just about feel the force from the 1,000 kilogram object. So we all have this force, but sometimes it's so small that we just consider it zero. Okay? But if you're wondering, is it possible that you could do an experiment and measure the force that I have on something, and you could just about, but it'd be very, very small. Okay. Gravitational force is what keeps you on Earth. It's the reason you don't float away.
Go up and down.
Down is okay, it's the up that's the problem. Yes. The gravity keeps you down, yes, it stops you going up, which is the problem. Now, we call the weight of an object, does anyone know, actually from high school, the weight of an object?
Like the push on.
Yeah, it's the gravitational force. It's how much force the Earth is pulling down. So it's the amount of gravitational force. So for example, here is the Earth, and here I am on the Earth, and the Earth is pulling me down with a force. And this force, we also call it the weight.
Yeah.
Pulling you down. So the weight is basically the gravitational force. That's what it is. Write this down. Yeah? Okay. Good stuff. Let's find a formula for weight. And there's nothing really special about it. For example, here is the mass, and this mass has a downward acceleration, and we know what the acceleration is. What is it? Minus 9.81, or in other words, minus g. So the force here is equal to ma, and what's the a here? G, or minus g. But if we don't care about the minus, if we just say the weight is mg, and we can say, of course, that this is going down, so we don't need to put the minus in. Yeah. There is a minus there, but you can just, we understand that the weight is going down, so we don't need to write the minus every time. We just need to write it when we're doing a calculation. Okay. But anyways, that's it. The formula, the weight is mass multiplied by 9.81. So for example, if we have 10 kilograms, what's the weight here?
10 multiplied by 9.8.
Yeah, so 98.1 newtons then, yeah. So all I need really is the formula here. Weight equals mg. Okay, you have that?
Yeah.
W is the weight, m is the mass, and g is the acceleration due to gravity. Right, try this one very quick for me, please. How much does a 2 kilogram physics book weigh on Earth? 19.6 Newton, thank you. And how did you get this? Good. Next example. How much does a 2 kilogram physics book weigh on the moon? Assume the acceleration due to gravity on the moon is 6 times smaller than the Earth. So your g is 6 times smaller on the moon. Something like that. Is it? For what? Divide by 6. Oh, sorry, you're giving me the next one. Yeah. So what did you get for the force then?
3.27.
Yeah, 3.27 newtons. Yeah. Yes. What did you get for the g on the moon?
G is 9.
No, it's not. On the moon.
9.81 multiplied by 1/6.
I did it all together, so I did.
Yeah, divide by, oh, okay, yeah, divide by 6, yeah.
I guess the previous answer then divided by 6.
1.63.
Oh, okay. That works, but I don't like it. But it works, yeah.
It was like 2 and one name, that's why I had to.
Don't listen to him. He'll teach you bad things. Okay, so we're okay with this then?
Yeah.
A 2 kilogram physics book weighs 4 newtons on an asteroid. What is the mass of the book? 2. I'm tricking you here. It's 2 kilograms. Yeah. 2.
Divide.
No, nothing.
No, it says
It says it in the
2
question.
kilograms.
Oh my god.
Yeah.
What is the rest of the book?
Right. Now, which will hit the ground first?
At the same time.
The ball or the feather?
The ball.
If we didn't take the head is
Yeah, but I didn't say that. This is real life.
The
Okay,
ball.
the ball.
Real life, which hits the ground first?
The ball.
The ball.
Because it
Okay.
has big mass. Is it?
Nope. But it's worth looking at now because it's quite interesting. So we all know that the ball will hit the ground before the feather, obviously, because that's our day-to-day experience. But let's see what happens. We have our two. Let's look at our two situations. So there's the ball, and this is the feather. So here's the ball, and here's the feather. You know what a feather is. U-V-A-T-S. Let's say the U is 0 for both. We don't know the V. What's the A? Minus 9.81, and the A? Minus 9.81. The T? Well, that's what we want to know. And the S? Oh, let's just say it's 1 meter. So it'll be minus 1 and minus 1 because it starts here and it falls 1 meter. Okay. So in the first case, let's calculate the time. What formula could I use? V equals U plus AT. Oh no, wait, we don't know the V, so I can't use that one. What can I use? V squared? No, S equals UT plus a half A T squared. So that's 2 over 9.81 square root. That's the T. I don't even care what that is. Here, S equals UT plus a half AT squared. And here you also get T equals the same thing. Now that's not surprising it's the same because the information here is the same. So the answer should be the same. But in real life, will the answer be the same?
No.
No, and the reason for that is, yes, that's the reason. We said they both have the same acceleration because they both have the same force. And this is actually not true. This one has a weight, and this one has a weight. These weights are different, but in fact, that's okay if the weights are different. That won't. That's not what's causing the problem. What's causing the problem is that here, the feather has some air pushing up.
Yeah.
Yeah. Hey, do you need to come in here or?
Yeah, I was advised that we often clean and said it was free from 12 to 2.
Oh, sadly, she was sadly mistaken then.
What time are you free at then?
We're finishing here at 20 to.
Okay, that's fine, we'll come back up.
Is that okay? Alright, thanks. Okay. What was I saying? Oh yeah. So I guess we're getting new desks. Yeah, okay. So the weight is not a problem. The fact that the weight's different is not making it go faster or slower. What is doing it is that here there is air resistance from the feather.
Yeah.
It feels that. Whereas the bowling ball doesn't really have this.
Mm-hmm.
So this here is reducing the force. And what does force cause? Acceleration.
Yeah.
So what's going to happen to the acceleration for this? It'd be smaller. It'd be smaller. Will that take it longer or shorter to hit the ground? Longer, yeah. So what's happening here is that the feather has two forces. The bowling ball has one force. What's the force on the bowling ball? It's just the weight.
It's a weight.
And the feather?
Yeah,
The weight and the air resistance.
But the ball does not.
Ah, yeah, but it's so small we can ignore it, yeah. So the word we call for air resistance, we use these words in physics called thrust and drag. So thrust is what's helping it go forwards, and drag is what's trying to stop it. Yeah. So, the examples with the car, okay? If you put your foot down to go faster, where is this force coming from? It's coming from the engine. So you have thrust, you're going forwards. But the air is pushing back, and you have drag.
Air and road.
No, not actually the road, it's just the air really. Yeah, not really the road. So just the air is pushing you back. Yeah. I think if you can draw this, okay, because this is the vocabulary we use, thrust and drag. Yeah?
I forgot how to
Beautiful.
draw cars.
Well, look at his one there. It's a work of art.
Definitely not worse than mine. I'm not going to show it.
Thrust and drag. Okay. Which is usually bigger?
Thrust, right?
In fact, thrust is always bigger. Because if the drag was bigger, what would happen?
The drag will be
No. If the drag was bigger, what would the car be doing?
Going backwards?
Yeah. No, actually, no, I suppose that's not true. Sorry. No, the drag could be bigger, but that doesn't mean the car would be going backwards. That would mean the car would be slowing down.
Okay.
Yeah. Okay. Well, let's have a look at more of these anyways. Terminal velocity. Does anyone know this or heard of this before? Terminal velocity. So tell me this. If you put your foot down, hit the accelerator, car goes forward, will the car keep getting faster and faster? Will the car keep accelerating forever? It will reach some limit.
Yeah.
Why? Why does it reach this limit? What?
The engine can't make.
Cannot go fast.
But there's still the force from the engine, and the force makes you accelerate, so why does it stop accelerating?
Because the force stops at a certain point.
No, the force is still there from the engine.
Force is limited.
Or stopping. You can only push too much.
No. When the car has a force in the engine, let's say 1,000 newtons, okay? So the car here has 1,000 newtons, yeah, and it has a mass, let's say 1,000 kilograms, to make it easy. So you have F equals ma, so A equals F over m, so in this case it'll be 1,
Okay.
whatever. But the acceleration doesn't stay at 1 forever, it doesn't keep increasing. If the acceleration was 1, then what should happen is the car should keep getting faster and faster and faster, but it doesn't. At some point it stops. The acceleration stops. But why should it stop? The force is still there, and the mass is still there.
Because of the drag.
Because of the drag, yeah, you see,
Equal, maybe.
the mistake I'm making here in the picture is I'm not considering the drag. So, at the beginning the drag is 0, and the total force is 1,000 minus 0.
When you go faster.
When it goes faster, the drag increases. So, for example, it could be 1,000 minus 100, so then it's only 900. When it reaches its limit, what happens?
500 minus 500.
1,000 minus 1,000. The force is 0. No more force means no more accelerating. Yeah. The maximum speed is called the terminal velocity. It's the maximum velocity. Now, we usually just use it when we're talking about things that are falling. For example, you know, the person who jumps out of the plane.
Yes.
They accelerate, but at some point they reach a maximum speed. This is called the terminal velocity. Yeah? Yeah? Okay. Right. So here's our man jumping out of the plane. There's a weight, of course, pulling him down, and an air resistance or a drag pushing him up. And they're balanced, they're equal when he's at his terminal velocity. Yeah. The last point is a little difficult. Drag force is often proportional to speed term. So drag is, what I'm trying to say is drag is something that gets bigger as you get faster, which makes sense. You know, the faster you go, the more drag that you have. So it's not constant, it's changing. Right. Okay. I think I said this already actually. Yeah, I did this one. A car starts at rest and accelerates by a force from the engine. The driver keeps his foot down, but the car does not accelerate forever. Why not? because the drag will cancel the force. So we did this one already. Okay, a euro coin is dropped from a 100-meter building. How long would it take the coin to hit the ground? I want you to calculate this. So you have a coin and you drop it from a building of 100 meters height. How long would it take the coin to hit the ground? Can you calculate this for me, please? I don't think this is too difficult. UVATS.
So it will be 0.01.
That seems too small. Right, UVATS. U. V. Don't know. A. T is what we want, and S is minus 100. What will we use? S equals? S equals UT plus a half A T squared. What did you get?
20, then.
Yeah.
Volts.
So what's that? Yeah, but what's the value? Yeah, 5.2 I said. Yeah?
That's nice.
Yeah. Okay, is that okay?
Yes.
Yeah. Now, my next part is, if you really did this, would your answer be longer or shorter than this time?
Longer.
Longer. So this time is only if there's no air.
Oh, okay.
But if you really did this, it should be longer.
From 100 meter period.
Yeah. What do you think? This is too long?
I think it will be close before, like, it's not,
Are you basing this off of personal experience or what?
I'm having it in my.
It will definitely be more.
Definitely more. Probably like 5 seconds, I'd say.
We are having 4 seconds.
4.5.
Yeah.
But I think the true answer will be bigger than this
Yeah.
because the air resistance will
Yeah.
slow it down. Yeah.
It's logical to think about doing this without air. Because
I wouldn't say illogical. That sounds a bit harsh. Maybe not realistic. Be more accurate. What would you have to drop to make it more accurate? To make it closer to 4.51? I think a bowling ball, a rock, maybe like a dart or something.
Yeah.
Something like this. Yeah.
No,
Something. Yeah. Something that won't really float. Yeah. Now the next question I want to do is quite difficult. It's important. It's not as easy as these ones. So I want to take my time on the next one, and I want you to write it down carefully. Okay. So just write it down, but don't do it. It's quite difficult. So write it down carefully. What have we got? Yeah.
this one?
This one here, please. Yes.
What's a big?
Like a cup, a cylinder cup, like using the lab, like a tall, narrow cylinder, tall, narrow cup. Yeah. Okay, nearly have this, yeah? Mir, you wrote this down?
Yes.
Carefully? Accurately?
Good.
You have this, yeah? Yeah.
Have to do.
Oh, not yet. No. That's later. The density is important, but not what we're looking at now. Okay, Andy?
Yeah.
Yeah, you ready? Yeah. Okay, so just before I started, just to make something really, really clear with Newton's. Do you need to write this down? Where are you in it?
After the ball, it takes
10 seconds for the steel ball to reach the bottom of the beaker. Yeah. So I just want to make something very clear with Newton's second law, F equals ma. Okay, that F is the total force. So when I say F equals ma, that is the total, or what's also called the net force. So what I mean, for example, yeah, that's okay. If this is 20 newtons, and this is 5 newtons, we say for this the F is 15 newtons.
Yeah.
Or if that was a 20 there, and there was a 20 here, then what would it be?
35.
Very good, it'd be 35 newtons. Because this is a plus, this is a plus, and this is a minus. Do you understand that this F is a total of all the forces added together? Is that okay? Yeah, we're happy with that? Yeah. Do you have that now, Mahmoud? I can put it back on the screen. There you go. You have it? Okay. Right, so you're all clear that in Newton's second law it's total force or net force. Okay, so let's have a look at this one. Right, so this is our beaker. How tall did I say it was?
8
centimeters.
No, the height.
8.
Oh, 18 centimeters.
0.8 meters. Okay, great. And it's full of some liquid. And there's a ball on the top, and I think I give you the mass, don't I? 0.1 kilogram. And I tell you how long it takes to hit the bottom.
10 seconds.
It takes 10 seconds. Okay, so is this picture in your mind? Now, 80 centimeters is how much? It's about, I would say like this much, yeah? About this. Okay? So if I drop a ball from here, should it take 10 seconds to hit here? No. But the reason it takes 10 seconds is the water resistance, the drag. Yeah. So what we'll do first is we'll calculate the acceleration. Will it be a big number or a small number?
Small.
Very small, I think, yeah. So let's calculate that first. U, what is it? 0. V, I don't know. A, not 9.81. Definitely not. It's something we don't know. T, we do know. S, minus 10. It's going down. Yeah, because we're taking here at the start.
Minus 8. 0.8.
Oh, sorry, yeah, the heck. That's why you looked confused at me. 0.8. 0.8. Yeah, good. Okay. So let's calculate the A. What formula could we use? Not B squared. S equals again? Yeah, so S equals UT plus a half A t squared, which is 100. 50, so it's going to be very small. A equals minus 0.016 meters per second squared. Okay, so write this much down. You got that? Yeah. Now, how can I calculate the drag? So, here's the small complication. Do you have this? Yeah. The drag force here at the beginning, what is it?
0.
It's 0 at the beginning, isn't it? And what is at the end? Well, not 0, because it's in the water. It'll be quite big. So I'll just write big here. Here it has a weight. I'll call it W. And here it has the same weight. Yeah? So the problem is the drag is changing. It's not constant. So for this question, that's why I said calculate the average drag, okay? So the average drag will be some number between 0 and the number at the end. It's an average. It's you know, it's not the real answer. It's just roughly the answer because it's too difficult. It keeps changing. We have to make it a constant. Okay. So if we look at the ball, there are two forces acting. The first one is the weight, which is mg, and the second one is the drag. Yeah? So what's the total force here?
mg minus.
Yeah, mg minus drag. If you take the down as positive, or if you take the down as negative, it'll be the other way, minus mg plus drag. Although it doesn't matter too much. Do we know the m? We do.
Yeah.
Do we know g? We do.
Yeah.
Do we know drag? No. Do we know f, the force?
Yeah.
No. Well, we could know it.
What's
9.81.
Acceleration?
Yeah. Now the weight is still mg, even though the acceleration is not g. Yeah. Okay. We can know the f by using what formula? ma. So we can say ma equals minus mg plus the drag. So that means ma plus mg is the drag. Or if you want, you can take the m outside. Ma plus g. Now what's the m?
0.8.
No, was it 0.8 kilograms? Yeah, okay. And I thought it was the distance.
No, it's 100 grams.
So 0.1.
Yeah.
What's the a? Minus
Minus
0.016. And the g?
Minus 9.
Plus 9.81. Yeah. So we can work out the drag. .9794 newtons. Yeah. Is that okay? Hey!
Hello. I'm just going to stick my head in the door. Fire notices were safe.
Really?
Well, they're not necessarily safe, but I'm
Yeah.
covered. So I'm
Oh,
safe.
okay.
We get inspected.
That makes more sense, because I think we'll know what to do if there's a fire, right? It's straight out the window. Yeah, okay, so we're good here. Yeah. I don't think it's too far to the
We'll
ground.
calculate and
We can test out that falling problem earlier, yeah. And those lads were around earlier for the tables. They seem to be under the impression that you told them the room's free now. Isn't that what they
I
said?
gave a very detailed timetable saying 103.
Must have confused them. So I told them to come back at 20 to.
Yeah,
I don't know if there's a class at 1 o'clock,
there
but
probably is, there should be.
there's 20 minutes in between them. Anything
Oh.
else?
No, fine.
Yes.
Exactly,
Yes, okay. Oh, well, look, the tables are here anyway, so.
Okay, that's fair. And they do make a huge difference in the classroom.
But they're kind of. What's the difference? Are they a bit smaller or?
No, it's just that they're going to be uniform. And
Oh yeah, I suppose. Yeah.
I mean, you saw the difference in making the desks in the other classrooms the same colour. It makes a huge difference.
I don't think any of us noticed it.
Well, that's boys for you.
Yeah.
I'll tell you, if you wore tights, you know the tights thing, because everybody is catching their tights.
I would never,
Yeah, but I mean,
I have learned something now.
It just looks inconsistent, and that's gonna fix it.
Okay. Yes,
I
okay.
think.
Okay, alright,
The
right.
girls will know.
Okay, alright, fair enough.
See you later, guys.
See ya. Okay, are we happy with that example then? I know it's a bit difficult. Zoom out? Yeah, okay. Please write it down carefully, okay? Did you write it all down?
No.
Yeah, please, carefully now, carefully. It's an interesting one, I think. It's interesting. And it would be a difficult one.
Yeah.
You wrote this down carefully.
Yes.
Yeah. You have to be very careful with the signs, okay? It's okay if you... Yeah, well, it's okay if you... I think Adnan, wasn't it? Or was it you? Yeah, I think it was you. You were gonna do mg minus drag. Now that's fine, but just take care that if you do that, what you're saying is down is positive and up is negative, which is fine. But it just means for your f, you would have to use not minus. You would have to use plus, because you're saying that down is plus. Do you get what I'm saying? So it's okay, but you need to be consistent. So if you do this, then this becomes a plus for you. Yeah. Okay, but this is fine, you know.
So like this always when it's down the snip.
No. What I'm saying is, the most important thing is that you're consistent. Do you know this word?
Right. The same. Yeah.
Yeah. So if you call down plus, then you must do that for the whole question. But since I started this question by calling down negative, then I must continue doing that. That is most important, not if you call it negative. Okay? Is this okay? I know it's quite difficult. Okay? I know it's a bit difficult. And then actually, the homework questions, I'm sorry to tell you, they're actually a little more difficult than this. Okay? So I think the homework might be a bit tricky. Let's have a look here at this.
On the website. Yeah.
Oh yes, yeah.
Okay, which page?
It'd be the next one. It'd be called weight.
And the homework is
Yeah, I'll show you just to double check. Does anyone want to take a picture on their phone to have it on their phone? Okay.
This one, yes?
But why don't you like using the PDF on Moodle?
No, like,
What?
it's hard on laptop, like, to open and then search and, like, what's done.
Oh.
It says your password.
Oh.
Actually, I find it more convenient.
Oh, that
Me too.
sounds terrible. You have to open the PDF. No, sorry. You have to go to Moodle, open the PDF. Oh yeah, and then you have to do this.
No, you should.
And then you have to
you should have a
turn it
habit of-
on.
I'm having
so much energy wasted.
password is there in my.
Yeah,
So
me
it-
too.
I don't know if students are getting lazier or I don't know.
They are, I can tell you that.
Okay, so we have to do two homework.
You know, like your parents had to carry their books to school every day, and
Yeah, so agree.
okay, all right, yeah. Yeah. You should be happy that it's electronic. You
Yeah.
should be like, oh, this is great. I'm going to open it up.
Yeah, it is very convenient.
It's very convenient, yeah. Okay, so like I said, the first few examples I did were quite easy. But unfortunately, it's more, the homework is more like the last example. That the easy examples are just to warm you up. Get the main idea. Yeah, it should be on Moodle. I don't really need to check it, do I? It should be just called Wait. Actually, I do want to check. I made a little program last night. I want to see if it's working. I'll show it to you. Maybe you'll find it.
You made a program last night?
I did. I made one last night because I was bored and I thought I'm going.
Easy. Exactly.
Hang on. Let's see if this works, or if it broke overnight. Did it work? It's not working. It was working last night. So I made a program that checks the bus times at this bus stop and then tweets it every minute. Yeah, but it's not working. It was working last night. Something was wrong. Yeah. So it annoys me that the buses sometimes disappear. So I made a Twitter account. Hi, I'm bus stop for the 15A and B, and it makes me so sad that these buses are unreliable. So I was gonna have it tweet every minute the bus times, so that you could see if the bus disappears. You know, like it says, bus is due in 10 minutes, 9 minutes, 8 minutes. Poof, it's gone. Yeah.
That happened to that one as well.
Yeah.
Which bus is that?
15A. It's the 15A.
1, 2,
from
2?
city center.
That's not too bad. This one's the worst.
I have this app on my phone.
You don't have this app because I think this one.
No, 15A. If you get it from the name street, it's always late.
Terrible.
Yeah.
Is it
Terrible.
hard to like make stuff like that?
It's a bit tricky at first, you know, but what the program does is it goes to Dublin Bus, it gets the bus times, and then it goes to Twitter, and then it tweets the times.
So
It's
Not
done
too bad.
automatically.
Yeah, well, it was working last night, and then it stopped working. But I don't know if my server's down, because I have a website with a I don't know if my server's down. I have a little web server for my website at home. Oh no, it's working. Yeah. The uptime is not great because the internet sometimes goes out for like yesterday I noticed the internet was gone between 7 a.m. and 9 a.m. The provider's not 100%.
Yeah, I mean that.
Yeah. Yeah, so anyways, I'll have to fix that when I go home now. I was excited that it would be working. It was working last night, so something went wrong overnight with it. Okay, so Moodle, the homework should be there.
We are having 2 homeworks.
It's 2 homeworks, and I'm telling you now, the second homework is difficult. So please make sure you give yourself enough time to do it, okay? Don't leave it until tomorrow night.
If somebody couldn't do it, like, he tried his best to do it, but he couldn't.
That's all I care about. Yeah.
Try.
As long as you try. Okay, we'll finish there, so, okay? Alright, see you Friday then.